Hi, welcome to part 2 of EEE 107, lecture 2. It's still in the frequency domain of the representation of signals. In the previous meeting, we talked about the Fourier series. So now, we will be talking about its generalization, the Fourier transform. If the series caters to periodic signals, then your Fourier transform caters to aperiodic signals. I can think of aperiodic signals as this: a periodic signal whose t, fundamental period, approaches infinity, or whose fundamental frequency approaches 0. Okay, so the aperiodic signal is just a generalization of your periodic signal, where your fundamental period approaches infinity. So what will be the implications of that? So just a review of the previous lecture. The synthesis equation, we use the synthesis equation to represent any periodic signal in terms of its complex weights. Okay? So these are the weights of the sinusoid depending on their frequency. The analysis equation is used to obtain these coefficients, these weights, these complex weights, given your periodic signal. Okay? The line spectrum, or the frequency domain, can be used to graphically represent your periodic signal in terms of its magnitude and phase. And we've also related the coefficients to the average power of your x of t using Parseval's power theorem. We'll also do all of this in this section for the Fourier series. The Fourier transform, rather. The Fourier transform also has some form of synthesis, some form of analysis, has its magnitude and phase spectrum, and it also has its own power theorem, how to relate the power of your aperiodic signal to your frequency spectrum. Okay? So the Fourier transform, the frequency domain representation of any signal, any aperiodic signal, or even a periodic signal actually, can be obtained using the Fourier transform. The Fourier transform and its inverse, the inverse Fourier transform, provides what we call a one-to-one mapping between the time domain and the frequency domain. So you have a time domain signal and a frequency domain signal. Okay? So we can actually derive the Fourier transform from the Fourier series. So if you have an aperiodic signal x of t with a finite duration, right here, you can create a Fourier series, or you can create a periodic signal by repeating the same signal over and over again at fixed intervals. Okay? So the fixed interval would create some form of periodicity to your aperiodic signal. What happens then is its frequency spectrum will be quote-unquote sampled. So parts of its frequency spectrum will pop up in its the continuous the continuous frequency spectrum of your aperiodic signal would now become discrete. Okay? So basically, if you have a periodic signal, as we have shown in the previous meeting, you get a discrete Fourier transform. Okay? You have a discrete or a series of delta functions to represent your periodic signal in the frequency domain. Now, if your signal is aperiodic, your Fourier transform will now be continuous. Okay? And we'll see actually that the process is also reversible. If you have a discrete signal, then you have a periodic Fourier transform. If you have a continuous signal, you have an aperiodic Fourier transform, or inverse Fourier transform for that matter. This will be demonstrated in the later part of this lecture. Okay? So this is how the Fourier series relates to the Fourier transform. The envelope of your Fourier series actually represents the Fourier transform if the signal becomes aperiodic. Okay? So now if we let t naught approach infinity, okay, as you see here, when we have a period t naught, okay, if we have a period t naught, then the spaces between your discrete functions or discrete signals right here is related to 1 over t naught. So the space between them is 1 over t naught. Now if t naught approaches infinity, then 1 over t naught approaches 0. That means you get the whole package right here as the Fourier series of your aperiodic signal. It's actually now called Fourier Transform. Okay. So in this limiting case, where your t naught approaches infinity, then this analysis equation becomes this. Your kt over t naught will just become some frequency f. Okay, since t naught approaches infinity, your k also approaches some infinity. Sorry, your k over t naught right here will just become some finite value f. And your synthesis equation, instead of being a summation, okay, this will now become an integral, since your c sub k will now be a function of f instead of a discrete series. Okay, and the derivation, you just access this link. Okay, so basically we can derive the Fourier transform from the Fourier series by assuming the period of your signal approaches infinity. And with that, what happens is your Fourier transform, or your line spectrum, becomes continuous. And that's what I mentioned earlier. Example, solve the Fourier transform of the following signal. So recall in the previous lecture, we solved for the Fourier series of a rectangular pulse train. And that rectangular pulse train, if you take one pulse and you just isolate it and make this t naught approach infinity, then you get your rectangular pulse function right here, which is defined by this. Okay, and to get its Fourier transform, just use the analysis equation. So it's this one, and you will get this Fourier transform of the rectangular pulse, which is closely related to c sub k. The c sub k is expressed as sinc in the previous lecture, as I've shown you. Okay, and if you sample that, depending on the frequency of, or the period of your rectangular pulse train, you get your Fourier series of your periodic rectangular pulse train. And that's how the the Fourier transform and Fourier series relate to one another. Okay, so if you get the Fourier transform of a rectangular pulse, you get a sinc function for its magnitude. Okay, just some note. Majority of its frequency content is concentrated from this interval right here. So it's right here where you get the most power. Right. If you have a smaller pulse width, then this lobe here increases. Right? And in reality, your x of f occupies an infinite bandwidth, since the sinc function just dies down but never goes to 0 outside this big lobe right here. Okay. And actually, you can observe an inverse relationship between time and frequency. If you have a finite time, so your signal is in finite time, then your frequency content is infinite. The bandwidth becomes infinite. Okay? Inversely, if your frequency content is finite, then the duration of your pulse becomes infinity. Okay? Now, if you scale the duration, let's say you want to decrease the duration, the bandwidth increases. And this is called the scale change property of your Fourier transform. If you scale in time, let's say you want to decrease the pulse width, then the bandwidth increases. Okay? And this creates the property of all signals that it cannot be both time limited and band limited at the same time. Okay? It cannot be time limited and band limited at the same time. So if you have a finite with pulse, a finite width, pulse of a finite width, pulse of a finite duration, the bandwidth it occupies is actually infinite. Conversely, okay, if you have a bandwidth, inversely, if you have a bandwidth that is finite, its time duration is infinite. Okay? And that is a fundamental property of any real signal. Okay? So this is the effect. Okay. So now let's move on to a semblance of the Parseval's power theorem in our aperiodic signals, the Rayleighs energy theorem. We define the signal energy as below for a finite duration pulse. Okay, so since the pulse has a finite duration, then the energy becomes finite. Okay, so this becomes an energy signal instead of a power signal. It doesn't have power or it has zero average power since T0 approaches infinity, and recall that the power is equal to 1 over T0 integral blah 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 blah. So this becomes 0 because of this. Instead, your signal has energy, finite energy. So we define the energy as you see here. And according to Rayleighs energy theorem, the area under the curve of the magnitude square of your signal in the time domain is equal to the area under the curve in the frequency domain. That's it. So it's actually kind of similar to Parseval's power theorem, where the average power is this, which is the summation of the weights. Okay. Well, if you think about it, the weights can form a line spectrum with delta functions. If you get the total area covered by these delta functions, it's just the same as getting the sum. So generally then, even for a Fourier transform signal or a Fourier series signal, generally the area under the curve in the time domain, the square, okay, is equal to the area under the curve in the frequency domain, magnitude squared. So this is a general case of the Parseval power theorem. Okay, and we call this right here the energy spectral density of the signal, which will be important when we're dealing with communication systems or we're dealing with communication signals. Because if we're trying to transmit a signal, we always need to think about how much energy it will consume in different parts of the frequency. So it's not just how much energy or the total energy it consumes. We are also concerned with how much energy or how much spectrum, frequency spectrum, it occupies. Okay? And I want you to realize now that spectrum is a precious resource. So the spectrum is a precious resource. We want to be efficient in using the frequency spectrum. Okay? So now we can now define, depending on periodicity, We can now define a power signal and an energy signal. So we can differentiate them. A power signal has a finite non-zero signal power. This means that the energy of the signal approaches infinity. So if we try to get the energy of this sinusoid, the square version of the sinusoid looks like this. If we integrate that over time, then we get infinite energy. But it has a finite power. Therefore, this is a power signal. Now, if your power is equal to 0, but your energy is less than infinity, then you have a finite signal energy, which gives rise to an energy signal. So a signal can be a power signal, an energy signal, or neither type. It cannot be both. So if you have a finite signal energy, you're already sure that the power is equal to 0. If your power is non-zero and finite, then its energy will be equal to infinity. And if its power is infinity, then it's neither a power signal or an energy signal. So it cannot be both. Okay. So now let's move on to the properties of a Fourier transform. So just to refresh your memory, this will be important in analyzing the different communication signals, just to refresh your memory then. So let v of t and v of f be a Fourier transform pair. What does that mean? The Fourier transform of v of t is v of f, and the inverse Fourier transform of v of f is v of t. So if z of t is equal to v of t, that means a time signal has the same shape as the frequency spectrum of v of t. Then if we get the Fourier transform of this, it's equal to this, but flipped. Okay? And this is due to the similarity of the Fourier transform equation and the inverse Fourier transform equation, or integrals. So this is actually a handy way of generating Fourier transform pairs without your the handy labor of integration. If you try to integrate signals, it's just very difficult, right? So other properties of Fourier transform, the linearity property. If a signal is equal to a weighted sum of two different signals, the Fourier transform of that same signal is the same weighted sum of the Fourier transform of the two signals, the individual Fourier transforms of the two signals. The effect of time delay, right here, is basically just a phase shift. So if you get the magnitude of this, it's still the same. So a time delay does not affect the magnitude spectrum, but the phase shift is there. And the phase shift is dependent on the frequency. Okay? So only the phase is affected and it's dependent on the frequency. Frequency scaling and time scaling, I've shown you that earlier. Okay? If you compress in time, you expand in frequency and vice versa. Frequency translation can be achieved by multiplying a complex sinusoid in time. And you get a frequency shift. If, for example, this is your v of f, then by multiplying a complex sinusoid in the time domain, you can shift this v of f to a different part of the frequency spectrum. Okay? And you can derive this using the duality theorem and the time delay property. And an important part or important property of your Fourier transform is the modulation theorem. So what is the modulation theorem? If you multiply v of t to a cosine function, so we denote this sometimes or most of the time in communication jargon, the carrier signal. What happens to the time domain expression, it can be expressed as this because of the property of your cosine function. Euler property, the Euler property of your cosine function. If you get the Fourier transform of these individual signals using the frequency translation property, you get this equation right here. So what does it do? If your original spectrum looks like this, what happens is the magnitude spectrum, the cosine function shifts it and splits it into two different subparts. Okay? You have a negative side and a positive side of your spectrum. And this will be important when we're going to talk about up conversion and down conversion of signals. Okay? So your spectrum is kind of translated by plus Fc and minus Fc respectively, where Fc is the frequency of your cosine function. And this is an important part or important property for your communication signals. Okay? And finally, I guess this is finally, nope, not yet. Differentiation in time multiplies a j2 pi f v of f right here. This is called frequency discrimination. Or it's the same as a first order high pass filter. The higher the frequency, the higher the output magnitude. Integration in time has the opposite effect, where you divide a j2 pi f here, and it's kind of like a low pass filter in which the higher the frequency, the lower the magnitude of the output. And finally, we have the convolution theorem. And this is a handy way of analyzing your signals, especially in your communication signals where you pass through a lot of system blocks. So since we're talking about a linear time invariant system, we're going to be talking about convolution a lot, and we don't want to convolve, right? It's a difficult process. In the frequency domain, a convolution in the time domain will result into a multiplication in the frequency domain, and vice versa, because of the duality theorem. And this is what happens. If your signal passes through a block with an impulse response of h of t, the output will be the convolution of h of t and x of t. In the frequency domain, you'll just multiply that. And you can easily get the output by using the inverse Fourier transform. Okay, and that's it. So that's the end of the second part of lecture 2. If you have any questions or if you need any clarifications, do not hesitate to leave a comment in the comment section below.